Hello everyone, welcome to our discussion of section 8.7 where we will be talking about Taylor and Maclaurin series. Now, Maclaurin series is just a special case of the Taylor series, and all of these series are tools for us to be able to integrate or differentiate or simply compute complicated functions easier, because series like Taylor series or a special case of it, which is the Maclaurin series, allow us to rewrite complicated functions in terms of polynomials. And polynomials are really easy to manipulate in every way, computing them, integrating them, differentiating them, and so on. Now, before we get to the nitty-gritty parts of this topic, I wanted you to have a good conceptual idea about what is it that we're actually doing with Taylor series approximation of functions. And I was able to find on YouTube a really good video, and the video is a little bit over 22 minutes long, but the first 14 minutes and 24 seconds of it are worth a look. So I've integrated that part of the video in this presentation, but because it's the first time I'm doing this, I don't really know how the audio and video are going to record as part of this lecture. So because I don't know that, just in case it doesn't turn out well, I might have to delete it. And so you will see, for that 14 minutes and 24 seconds, you're not going to see this video basically. Instead, I will give you the reference so you can then go and watch the YouTube video on YouTube on your own, in which case you're not going to have these any audio or video issues with it. But because I'm integrating it within this module here, I don't know how the sound and audio will look within this presentation. So just please bear with me. If you don't, I'm letting you know that it's coming up as part of this present lecture. But if you don't see it, it means that the audio or video didn't record properly and I had to delete that portion of it. So here we go. So for the next 14 minutes and 24 seconds, I hope this video is helpful to give you an idea about the conceptual understanding of what is it that Taylor series actually is meant to do, or what is it that it does.
When I first learned about Taylor series, I definitely didn't appreciate just how important they are. But time and time again, they come up in math and physics and many fields of engineering because they're one of the most powerful tools that math has to offer for approximating functions. I think one of the first times this clicked for me as a student was not in a calculus class, but a physics class. We were studying a certain problem that had to do with the potential energy of a pendulum. And for that, you need an expression for how high the weight of the pendulum is above its lowest point. And when you work that out, it comes out to be proportional to 1 minus the cosine of the angle between the pendulum and the vertical. Now, the specifics of the problem we were trying to solve are beyond the point here. But what I'll say is that this cosine function made the problem awkward and unwieldy, and it made it less clear how pendulums relate to other oscillating phenomena. But if you approximate cosine of theta as 1 minus theta squared over 2, of all things, everything just fell into place much more easily. Now, if you've never seen anything like this before, an approximation like that might seem completely out of left field. I mean, if you graph cosine of theta along with this function, 1 minus theta squared over 2, they do seem rather close to each other, at least for small angles near 0. But how would you even think to make this approximation? And how would you find that particular quadratic? The study of Taylor series is largely about taking non-polynomial functions and finding polynomials that approximate them near some input. And the motive here is that polynomials tend to be much easier to deal with than other functions. They're easier to compute, easier to take derivatives, easier to integrate, just all around more friendly. So let's take a look at that function, cosine of x, and really take a moment to think about how you might construct a quadratic approximation near x equals 0. That is, among all of the possible polynomials that look like c0 plus c1 times x plus c2 times x squared, for some choice of these constants, c0, c1, and c2, find the one that most resembles cosine of x near x equals 0, whose graph kind of spoons with the graph of cosine x at that point. Well, first of all, at the input 0, the value of cosine of x is 1. So if our approximation is going to be any good at all, it should also equal 1 at the input x equals 0. Plugging in 0 just results in whatever c0 is, so we can set that equal to 1. This leaves us free to choose constants c1 and c2 to make this approximation as good as we can, but nothing we do with them is going to change the fact that the polynomial equals 1 at x equals 0. Now, it would also be good if our approximation had the same tangent slope as cosine x at this point of interest. Otherwise, the approximation drifts away from the cosine graph much faster than it needs to. The derivative of cosine is negative sine, and at x equals 0, that equals 0, meaning the tangent line is perfectly flat. On the other hand, when you work out the derivative of our quadratic, you get c1 plus 2 times c2 times x. At x equals 0, this just equals whatever we choose for c1. So this constant c1 has complete control over the derivative of our approximation around x equals 0. Setting it equal to 0 ensures that our approximation also has a flat tangent line at this point. And this leaves us free to change c2. But the value and the slope of our polynomial at x equals 0 are locked in place to match that of cosine. The final thing to take advantage of is the fact that the cosine graph curves downward above x equals 0. It has a negative second derivative. Or in other words, even though the rate of change is 0 at that point, the rate of change itself is decreasing around that point. Specifically, since its derivative is negative sine of x, its second derivative is negative cosine of x, and at x equals 0, that equals negative 1. Now, in the same way that we wanted the derivative of our approximation to match that of the cosine, so that their values wouldn't drift apart needlessly quickly, making sure that their second derivatives match will ensure that they curve at the same rate, that the slope of our polynomial doesn't drift away from the slope of cosine x any more quickly than it needs to. Pulling up the same derivative we had before, and then taking its derivative, we see that the second derivative of this polynomial is exactly 2 times c2. So to make sure that this second derivative also equals negative 1 at x equals 0, 2 times c2 has to be negative 1, meaning c2 itself should be negative 1/2. And this gives us the approximation 1 plus 0x minus 1/2 x squared. And to get a feel for how good it is, if you estimate, say, cosine of 0.1 using this polynomial, you'd estimate it to be 0.995. And this is the true value of cosine of 0.1. It's a really good approximation. Take a moment to reflect on what just happened. You had 3 degrees of freedom with this quadratic approximation, the constants c0, c1, and c2. c0 was responsible for making sure that the output of the approximation matches that of cosine x at x equals 0. c1 was in charge of making sure that the derivatives match at that point. And c2 was responsible for making sure that the second derivatives match up. This ensures that the way your approximation changes as you move away from x equals 0, and the way that the rate of change itself changes, is as similar as possible to the behavior of cosine x, given the amount of control that you have. You could give yourself more control by allowing more terms in your polynomial and matching higher order derivatives. For example, let's say you added on the term c3 times x cubed for some constant c3. Well, in that case, if you take the third derivative of a cubic polynomial, anything that's quadratic or smaller goes to 0. And as for that last term, after 3 iterations of the power rule, it looks like 1 times 2 times 3 times whatever c3 is. On the other hand, the third derivative of cosine x comes out to sine of x, which equals 0 at x equals 0. So to make sure that the third derivatives match, the constant c3 should be 0. Or in other words, not only is 1 minus 1/2 x squared the best possible quadratic approximation of cosine, it's also the best possible cubic approximation. You can actually make an improvement by adding on a fourth order term, c4 times x to the fourth. The fourth derivative of cosine is actually itself, which equals 1 at x equals 0. And what's the fourth derivative of our polynomial with this new term? Well, when you keep applying the power rule over and over, with those exponents all hopping down in front, you end up with 1 times 2 times 3 times 4 times c4, which is 24 times c4. So if we want this to match the fourth derivative of cosine x, which is 1, c4 has to be 1 over 24. And indeed, the polynomial 1 minus 1/2 x squared plus 1/24 times x to the fourth, which looks like this, is a very close approximation for cosine x around x equals 0. In any physics problem involving the cosine of a small angle, for example, predictions would be almost unnoticeably different if you substituted this polynomial for cosine of x. Now take a step back and notice a few things happening with this process. First of all, factorial terms come up very naturally in this process. When you take n successive derivatives of the function x to the n, letting the power rule just keep cascading on down, what you'll be left with is 1 times 2 times 3 on and on and on up to whatever n is. So you don't simply set the coefficients of the polynomial equal to whatever derivative you want. You have to divide by the appropriate factorial to cancel out this effect. For example, that x to the fourth coefficient was the fourth derivative of cosine, 1, but divided by 4 factorial, 24. The second thing to notice is that adding on new terms, like this c4 times x to the fourth, doesn't mess up what the old terms should be. And that's really important. For example, the second derivative of this polynomial at x equals 0 is still equal to 2 times the second coefficient, even after you introduce higher order terms. And it's because we're plugging in x equals 0. So the second derivative of any higher order term, which all include an x, will just wash away. And the same goes for any other derivative, which is why each derivative of a polynomial at x equals 0 is controlled by one and only one of the coefficients. If instead you were approximating near an input other than 0, like maybe x equals pi, in order to get the same effect, you would have to write your polynomial in terms of powers of x minus pi, or whatever input you're looking at. This makes it look noticeably more complicated, but all we're doing is just making sure that the point pi looks and behaves like 0, so that plugging in x equals pi is going to result in a lot of nice cancellation that leaves only one constant. And finally, on a more philosophical level, notice how what we're doing here is basically taking information about higher order derivatives of a function at a single point, and then translating that into information about the value of the function near that point. You can take as many derivatives of cosine as you want. It follows this nice cyclic pattern: cosine of x, negative sine of x, negative cosine, sine, and then repeat. And the value of each one of these is easy to compute at x equals 0. It gives this cyclic pattern 1, 0, negative 1, 0, and then repeat. And knowing the values of all of those higher order derivatives is a lot of information about cosine of x, even though it only involves plugging in a single number, x equals 0. So what we're doing is leveraging that information to get an approximation around this input. And you do it by creating a polynomial whose higher order derivatives are designed to match up with those of cosine, following this same 1, 0, negative 1, 0 cyclic pattern. And to do that, you just make each coefficient of the polynomial follow that same pattern, but you have to divide each one by the appropriate factorial. Like I mentioned before, this is what cancels out the cascading effect of many power rule applications. The polynomials you get by stopping this process at any point are called Taylor polynomials for cosine of x. More generally, and hence more abstractly, if we were dealing with some other function other than cosine, you would compute its derivative, its second derivative, and so on, getting as many terms as you'd like, and you would evaluate each one of them at x equals 0. Then, for the polynomial approximation, the coefficient of each x to the n term should be the value of the nth derivative of the function, evaluated at 0, but divided by n factorial. And this whole rather abstract formula is something that you'll likely see in any text or any course that touches on Taylor polynomials. And when you see it, I want you to think to yourself that that constant term ensures that the value of the polynomial matches with the value of f. The next term ensures that the slope of the polynomial matches the slope of the function at x equals 0. The next term ensures that the rate at which the slope changes is the same at that point, and so on, depending on how many terms you want. And the more terms you choose, the closer the approximation, but the trade-off is that the polynomial you'd get would be more complicated. And to make things even more general, if you wanted to approximate near some input other than 0, which we'll call a, you would write this polynomial in terms of powers of x minus a, and you would evaluate all the derivatives of f at that input, a. This is what Taylor polynomials look like in their fullest generality. Changing the value of a changes where this approximation is hugging the original function, where its higher order derivatives will be equal to those of the original function. One of the simplest meaningful examples of this is the function e to the x around the input x equals 0. Computing the derivatives is super nice as it gets, because the derivative of e to the x is itself. So the second derivative is also e to the x, as is its third, and so on. So at the point x equals 0, all of these are equal to 1. And what that means is our polynomial approximation should look like 1 plus 1 times x plus 1 over 2 times x squared plus 1 over 3 factorial times x cubed, and so on, depending on how many terms you want. These are the Taylor polynomials for e to the x.
All right, everyone. So this was the video, extent of the video that I had imported into this. I hope it recorded nicely so I don't have to remove it. Now, let me switch to the document camera so we can continue with our with the details of what Taylor series are and do. So here it is. As I promised you, the link to the video, you can just log into YouTube and search for this, Taylor series, Essence of Calculus. And the video that I just showed, the full video, which is a little bit over 22 minutes, should come up there. And it's by the YouTube channel that has that. It's called 3 Blue, 1 Brown. And he's got lots of awesome videos on various math topics. You can check those out whenever you have the time. So important points to take away from this video are these: that Taylor series is a way to use a polynomial to approximate the value of a function at a certain point a along the x-axis. And note that this approximation is only valid and good within a certain distance from a. We already know what that distance from a is, and we call it the radius of convergence for this series. So every time you use the series to approximate a function, you need to know how good that approximation is, and the way you know that is by determining the radius of convergence about the point that you've made the approximation. And this is for the Taylor series that we will look at or we will introduce in a few seconds. So that's one thing. The other thing is that we do this because polynomials such as Taylor series are easier to compute, differentiate, and integrate. And this is relative to how much more complicated it would be if we didn't use series. Okay, so having said that, then the Taylor series of the function f at a has this formula, and I have a little bit of a statement or details about it. It just describes what this formula, Taylor series formula is. We're basically taking a function that has a power series expansion at some value a along the x-axis. That is, if f can be represented by a power series that converges within a certain radius of convergence, which is defined by that. And we saw this in the previous section, 8.6. Then such a function must have a series form that looks like this. Now, the n factorial you're familiar with, the x minus a you're familiar with, and in the video that you saw, it referenced it as a being the point along the x-axis about which we're making this approximation. Because you can, for the special case, when a equals 0, you're making the approximation about x equals 0, which is the y-axis. So in essence, if you choose a to be 0, which would be the Maclaurin series that we'll see next, you're really finding a series that approximates the function at or around the y-intercept. That's what you're doing in effect. Now, the numerator here might look a little bit unfamiliar to you, but that's the nth derivative of the function that we are finding the Taylor series for. So that the nth derivative of that function at a, whichever point we're approximating. Okay, we'll see examples of this so you know exactly how all this works out. And here's a small expansion of that series, the Taylor series. So by the way, when that n is 0, then we're talking about evaluating the function itself at a. So that's not a derivative. F at 0, the 0th derivative of the function is the function itself evaluated at a. So that's just taking that function, evaluating it at a, and it'll give us f to 0 of a. Then the first derivative, which would be f prime, that we know how to calculate that, the first derivative, evaluated at a. If n is 2, that would be the second derivative, evaluated at a. If n is 3, that would be third derivative evaluated at a, and so on and so forth. And of course, the other terms change accordingly. Now, Maclaurin series is the Taylor series, but in the special case when a equals 0. So when that's the case, for the special case when a equals 0, so when we want to approximate a function by the Taylor series at the y-intercept of a function, the Taylor series becomes the Maclaurin series. Okay, maybe I should underline that. And you have the formula here. So you no longer have x minus a to n power, which we had with the Taylor series, right? X minus a to n power, and a being where each derivative would be evaluated. Now, for the Maclaurin series, each derivative is being evaluated at 0. And that. Okay? And here is again a small expansion of that formula. So for n equals 0, then we're talking about the function, original function evaluated at x equals 0. And then for the first derivative, if n equals 1, we're talking about the first derivative evaluated at 0 and incorporated or integrated with the rest of this term, divided by n factorial times x to the n power. If n is 2, we're talking about the second derivative evaluated at 0. And this is for the Maclaurin series. If n is 3, we're talking about the third derivative evaluated at 0 and integrated with the rest of this equation or these terms. So this is just a brief description of that, just to make sure that you know you are familiar with the notation. So f to 0 of x is the original function, and then the first derivative evaluated at whatever value, and the second derivative evaluated at that, and so on. I hope the material in this section doesn't overwhelm you. There's a whole bunch of things that we introduce as I talk about it here. I'm just introducing these. And then when we see actually examples at work, we're going to reference back this information. So you need to be familiar with it. So please make sure that you read the book section and also these lecture notes. Just be familiar what it's talking about, so that not to memorize them, but so that when you need to use them, you know where to look to reference this information. So here is an expression that is connected to the Taylor series, and we call that Taylor's formula. And it's also known as Lagrange's form of the remainder term. Basically what it's saying that suppose an nth degree Taylor polynomial that is being used to approximate a function, right, which is what we're doing with the Taylor polynomials. Let's call that nth degree Taylor polynomial as t sub n, which is approximating some function f of x at some point a. Then because this is an approximation, then we're going to have an error. And let's call that r sub n of x. And I'm using notations that your book uses, so when you read this and that, they merge and they make sense. So r of n represents the error due to using Taylor polynomial to approximate a function. Now we can write that original function precisely by setting it equal to the Taylor polynomial plus the error term, or the remainder as it is called. That error term plus the Taylor polynomial gives us the exact function that we started with. So, and of course, as the n goes to infinity in our Taylor polynomial, then that error approaches 0. Okay, so if we're using a few terms, as you'll see in some of the examples, then that error term is a little bit away from the 0, but it's still small. So as you saw in the video, Taylor polynomials are an excellent way to approximate functions that they apply to. But as n goes to infinity, then that error really drops to 0. And now within the interval of convergence, so the approximation of the Taylor series or any series of a function is only valid or good within that radius of convergence. So within that interval of convergence, which we have introduced as this in even section 8.6, there is a number, let's call it z. Your book calls it z, or most textbooks call it z. So in that interval which defines the interval of convergence within the radius of convergence, there is a number z such that the remainder term in the Taylor series is going to be given with this equation. So we can actually, if we're interested, we can quantify the error term from a Taylor series approximation of function. And here is a quick note. Note that the n plus 1th derivative, which is that term, this is the n plus 1th derivative, that's what that's referring to, of f in the numerator is evaluated as z, not a. And I say this because originally when we looked at the Taylor series formula, so the nth derivative was being evaluated at a, so is this one. So was this one, right, for the Taylor series itself. But for the error term, the derivative is evaluated at z. And oftentimes we don't really know what z is, but we're interested in finding out the interval where it's located. Okay, so we can approximate where it's located, but we don't really know what z exactly is. Next, we will look at some of the basic formulas that we will use in our examples and as a reference too. So we will look back at these in reference to solve the problems, example problems that are coming up. So here we have useful fact number 1, limit of x to the n over n factorial. You'll see this a lot in this maybe and also in Calc 3. For every, that limit approaches 0, which basically means that the denominator is growing much, much faster than the numerator is doing. And this is true for all real values of x. Useful fact number 2, the number e can be represented by this series from 0 to infinity of 1 over n factorial. Okay, and here in this table, and I guess I can't fit it all on screen, especially if I zoom in a little bit. I need to zoom in as we work on the examples. So there are 1, 2, 3, 4, 5, 6, 7 total formulas here, and these are important Maclaurin series and their radii of convergence. And this is, your book also has this, and I've included it here. So Maclaurin series, as we said, it's a special case of the Taylor series where that A is equal to 0. So we're taking the approximation, we're finding the approximation about the y-intercept, basically. That's what we're doing with the function that we're approximating. Okay, so they're here. We will reference these back. So let's look at our first example of applying the Taylor series. So here, it is saying find the Taylor series for f centered at 4. So a in this case is 4. If this is the nth derivative formula for the function that we have. So we have, what we have here is the fourth derivative expression for that function, not the original function itself. Okay, so let's begin by saying that, begin with the Taylor series formula. At a equals 4, is defined as the following. So we have the summation from 0 to infinity of the nth derivative at a divided by n factorial times x minus a to n power. So here in this Taylor series formula, we have a equals 4, right? Which is what we've been given. So then we have, given the Taylor series formula we have, all we have to do, so this is the entire expression that we have goes in the numerator of this Taylor series. That's what we have. We have the nth derivative evaluated at 4, or a equals 4, and that entire thing goes, all of this expression belongs here in the numerator, divided, of course, by n factorial, multiplied by x minus 4 to the n power. So let's just plug it in. I'm just plugging in this in the numerator of here. Maybe I should have put this a little bit lower, but I think it'll do. Divided by n factorial times x minus 4, right? A is 4. 2n power, which is part of the Taylor series. Now, if this is a complex fraction, so let's clean it up a little bit. Let's write it properly. We simply multiply the n factorial by this denominator. So we have 3 to the n power times n plus 1 times n factorial. And of course, this stays where it was. So can we simplify things? Absolutely. We can simplify this with this. And we end up with the Taylor series that we were asked, which is like that. So we have our Taylor series. So the other piece of information is that let's just find the radius of convergence for this series. So we have, so in addition to this, we're going to find the radius of convergence. So to find the radius of convergence, as we saw before in the previous sections, we have to apply the ratio test. Okay, we know how to do that. So limit as n goes to infinity of an plus 1 divided by an. In this case, an is all of this, and an plus 1 would be, whatever you see n, we just replace it with n plus 1. So this would be n plus 1, this would be n plus 1 plus 1, which would be n plus 2, and so on and so forth. Minus 1 to n plus 1 power, and times, I'm just going to put this in the numerator here, x minus 4 to n plus 1 power divided by 3 to the n plus 1, right? 3 to n plus 1 times n plus 1 plus 1, which would be n plus 2 here. Okay, then that divided by a sub n. A sub n is all of that. When we divide, we just flip the second fraction that we're dividing by, right? That's to simplify our complex fraction result. So I'm just going to put this on top and divide it by everything we have there. And all of that, of course, inside the absolute value. So I'm just going to check quickly here. Everything looks right. Okay, so now simplifying this a little bit, what do we get? So minus 1 to n power will cancel with this minus 1 to n power. In the numerator, we end up with minus 1, just the minus 1 to 1 power, which is minus 1. Then we have 3 to the n power plus 1. That 3 to the n will cancel with this. we are left with just a 3 in the denominator, and I should put that here. And then that would be 3 to the first power. And then what else do we have? So x minus 4 to the n will cancel with this x minus 4 to the n. We will have left just 1 x minus 4 to power 1. So I'm just going to put that here. Times, of course, n plus 1, which doesn't cancel. And in the denominator, we have that all canceled. This all canceled. The only thing we have left in addition to 3 to first power is just n plus 2. Okay, so now let us bring everything that is not relevant to n outside of the absolute value. So I will, hopefully I can show these like that. Okay, so that will give us positive 1 over 3. So we have, then we have also x minus 4 that we can pull out inside the absolute value. So x minus 4 inside the absolute value divided by, minus 1 just drops out, divided by 3 times, then we can take the limit of what is left inside. Limit as n goes to infinity of n plus 1 divided by n plus 2. Now notice that this is really because we're dealing with very large numbers here, n going to infinity, so in that context 1 and 2 are negligible. So really what we have here is this expression, x absolute value of x minus 4 over 3, limit of n goes to infinity, and this is just or we can treat it like we treated this in the previous section. Let's do that. It's more formal that way. So let's divide every term by the highest power of the n in the denominator, which is n over n plus 1 over n, n over n plus 2 over n, and then so we have 1 plus that. We don't need that anymore. And we have just a little more work left for us. 1 plus 1 over n and 1 plus 2 over n. As you apply the limit, these two terms drop out as 0 and we end up with just 1. So we have absolute value of x minus 4 divided by 3 times 1. Okay, so for the series that we came up with, for this series to converge, then the radius of convergence must be this quantity must be less than 1. And this is condition for the series to be convergent. Okay, so let's solve for that, use that to find the radius of convergence. So we have absolute value of x minus 4 less than 3. And so we have, from here, we know that a radius of convergence must be 3. And that's for a Taylor series that is about a equals 4. Okay. Okay, so let's see another example. We have here, they ask us, find the Maclaurin series for f of x using the definition of a Maclaurin series. Assume that f has a power series expansion. Of course, this is necessary for us to be able to apply the Taylor or Maclaurin series. Also find the associated radius of convergence. Okay, so the Maclaurin series, let us write that down. So the general formula that we have for it. Okay, so that's the Maclaurin series. Let's use this to find, because we need to, if we are to find the Maclaurin series, we need to know, we know what that is, x to the n, we know the n factorial, but we don't know what that expression should be. We need to find an expression here for that piece, for the numerator. And to do that, we ought to calculate a few of these to see the pattern. So we're going to calculate a few of these derivatives at 0 to find the pattern which we think we can then write as the other piece of this series. Okay, that's our goal. So let me actually write that here. A few terms of that quantity. To find this general pattern. So I will do that here in this corner in a table. All we need is just, so we have, let me just set up a table so we can organize that information. Like that. And we have, for n values, let's go up to 4. I think that would be sufficient in this case to find a pattern. So n here, and then we have the nth, we will find the nth derivative in x. And then once we have that, we will evaluate it at 0. Okay, in the next step. So we nth derivative evaluated as 0. And I guess I should separate these as well. So and a column here. So if we pick for n equals 0 and then 1, I guess 2, 3, and 4, and then of course this continues, right, because we have an infinite series. So the function, the 0 derivative means the original function. So, and the original function is just that, e to the minus 2x. So when n equals 0 here, in this notation, we have the function itself, like that. The first derivative, that's when n equals 1, we have the first derivative, so let's find that. That would be minus 2 times e to minus 2x. When n equals 2 in this notation, that means we're looking for the second derivative, so we're just going to take the derivative of this again. We will end up with positive 4e to minus 2x. When n equals 3 here, we're looking for the third derivative, which is simply taking the second derivative again, a third time, or the next one, third derivative with respect to the original function. So we have minus 8 times e to minus 2x power, and of course we need one more. When n equals 4, then we're looking for the fourth derivative of this function. So that would be minus 2 times minus 8, or positive 16 times e to minus 2x power. So now, in this column, we're going to evaluate each derivative when x equals 0. So what do we get here? We get e to minus 2 times 0, which would be e to the 0, and that'll give us 1. Then here we will have minus 2 times e to minus 2 times 0. This would be minus 2 times e to the 0, or minus 2 times 1, or minus 2. Here we have 4 times e to minus 2 times 0. This would be 4 times e to the 0, or 4 times 1, which is 4. And by the same token, we will end up with, notice the pattern, so we will end up with negative 8 and positive 16 for these. Now, if you look at the pattern, in these numbers with respect to n. When n was 0, this was 1. When n was 1, this was minus 2. So we have an alternating series, right? So we have to have a minus 1 to some power. Minus 1, let's say, to n. If minus 1 to n, the numbers that I've boxed give us the pattern that we're looking for. So we need to generalize this. When we generalize that, we're going to replace that with the generalized formula for the pattern we have for the derivatives evaluated at 0. Okay, that's what our goal is. So let me write this down here, and then I will rewrite this here, and then we will go from there. We will develop it based on the pattern we have here. So we have n factorial times x to the n. Again, we started with the Maclaurin series formula, okay, and now we're finding that expression. So let's see what the pattern is. So we have minus 1. When n equals 0, we have positive. So minus 1 to 0 power would give us a positive value. When n was 1, we had a negative number. So minus 1 to n would still be valid, right? Minus 1 to 1 will give us a negative. I'm just trying to generalize this algebraic sign, not the numbers yet. We will get to that next. So for the second term, when n equals 2, minus 1 to second power, we will have positive, and that's what we want. For the n equals 3, minus 1 to third power, we get minus 1, which is what we are looking for. So it looks like minus 1 to n power is the right pattern there. It's going to give us that. Now the numbers. So for the first digit, for n equals 0, we ended up with 1. For n equals 1, now disregard the algebraic signs. We already have that. We're looking for a pattern to model the digits, 1, 2, 4, 8, and 16. So then for n equals 1, we have 2. For n equals 2, we have 4. For n equals 3, we have 8. So that looks like the pattern for, and then for n equals 4, of course, we have 16. That would be the pattern for 2 to the n power. So we found a pattern that models the algebraic sign and the numbers in the various derivatives of the function evaluated at 0. Okay, so we will plug that here. We did that here, and then we can, of course, divide by n factorial and multiply by x to the n. Okay, and here is our series, Maclaurin series for that function. Okay, all right. So now they're asking us to find the associated radius of convergence. For that, we will have to apply the ratio test. So we have limit as n goes to infinity of n plus 1 divided by n. And of course, that will be everything you see here. For n, we will plug in n plus 1. So we have minus 1 to n plus 1, 2 to n plus 1, and divided by n plus 1 factorial times x. Well, I should have put the x there on top. It's okay. It doesn't matter that much. So it'll be easier to see what terms cancel. That's why I say that. So now that, maybe I can still do that like that. And then multiplied by, because we're dividing by a of n, and that would flip this fraction. So then n factorial divided by all of that, minus 1 to n power, 2 to the n power, and x to n power inside the absolute value. And sorry for that little bit miss there. But that's x times, all of that times x to n plus 1 power. So there's quite a bit that simplifies here. We have the minus 1 to n power. With this cancels out, we end up with minus 1 to just minus 1. And because that's inside the absolute value, it drops out anyway. The n plus 1 factorial, let's see. So we can that's this piece. This piece, as you know, it's n plus 1 times n factorial, right? We can rewrite that as that. And then the n factorials cancel out. We will end up with just n plus 1 in the denominator. And then 2 to the n, with this 2 to the n cancels out. We are left with just a 2 in the numerator. And then also an x in the numerator. So we will have these terms. We will have 2 to the x divided by n plus 1, just this, n plus 1. Okay, so now the 2x, we can just pull this out, and we have just 2 times absolute value of x, and all of that times limit as n goes to infinity of 1 over n plus 1, right? That's what's there. So, of course, as n goes to infinity, this whole term becomes 0. So 0 times 2 times absolute value of x is just 0. So we have 2 times absolute value of x times 0. That's just 0. And we know that that is less than 1, irrespective of any x term. So this is true for all x. For all x, and this means that the radius of convergence is infinity. Like that. Okay. So let's look at another example. This next example is going to be different, which is good. So we want to see various applications of our Taylor series. So this time we want to apply or find the Maclaurin series for this function. Of course, we also want to find the radius of convergence. So knowing that the Maclaurin series is this, well, I'll just put it here, maybe to save a little bit of space. Like that. And so once again, we want to, because we have the denominator, we have this x to the n, but we really need an expression for the numerator of this derivative, nth derivatives evaluated at 0. So let us find a pattern for that, just like the previous example. So let us find Okay, so once again, I think I better just draw a table here. So we have, oops, sorry. So we have n, maybe we'll do if 3 or 4, 0 to 3, 0, 1, 2, 3, and then so f, the nth derivative evaluated at x. So we want to calculate the derivatives, and then we want to calculate each derivative, of course, at 0, right, for the Maclaurin series. So to do that, let's do a few here, a few here. Okay, so our n's, we'll do 0, 1, 2, and 3, and of course this can continue as many times. Now the original function, when n equals 0, that's that's the original, that's the given function. So we simply write hyperbolic cosine of x, and then when n equals 1, we're dealing with the first derivative of this, the hyperbolic cosine, and the first derivative of hyperbolic cosine is hyperbolic sine. And then hyperbolic sine has the derivative for when n equals 2, we're looking for the second derivative of that. And that would be the next derivative after this one, n equals 1. So we are back again at hyperbolic cosine. And then if we repeat this for n equals 3, we will get hyperbolic sine again. Okay, so this will continue. And then each of these evaluated at 0, this will be 1, and this hyperbolic sine evaluated at 0, right? Each one of these derivatives evaluated at 0. It'll be 0, hyperbolic cosine evaluated at 0 will be 1, and the hyperbolic. So you can see that it's 1, 0, 1, 0. It's repeating itself again and again, like that. Okay, and this will repeat forever. Okay, so one thing to notice here is that, note that for these values, that notice that the pattern, or notice that the derivative evaluated at 0 is equal to 1 when n is even, and it's equal to 0 when n is odd. So let's write that down. That is equal to 1 if n is even, and equal to 0 if n is odd. So here, noticing that then, to find a pattern for that, we need to use a different method than what we did in the previous example. Okay, this is a little more complicated than that. So let me, over in the other one we just calculated a few numbers, and these numbers gave us the pattern. But here it won't be that apparent. So let's see what we can do. So here, we will have to find those terms differently. These terms, we will have to find them differently. Differently than in the previous example. So how would we have to do that then? Well, recall that, I guess recall from trigonometry, I think we introduced this, or maybe it was calculus 1. But one of those, but in the past, recall that, let me just say from trigonometry, I think that's where we first introduced this. Recall from trigonometry that f of, I mean, this is pretty important. So f of x equals hyperbolic cosine of x is equal to e to the x plus e to minus x divided by 2. And I guess resurrect these because we know we're dealing with Maclaurin series, and we know that in that table that I showed you, which your book also has, we have an expression for the Maclaurin series of e to the x. Okay, so we can make use of that information here in our table. Okay, so this formula will allow us to do that. Okay, so in other words, we can just say that that is, or let's rewrite that to 1/2 times e to the x plus e to the minus x. Okay, that same expression. So now, using the table, using the, I guess it's called table of important Maclaurin series. On page 5 here, and it's also on your book, in your book. Page 5 of these lecture notes. Okay, so we have e to the x equals series from 0 to infinity of x to the n divided by n factorial. Okay, and by the same token, so this means from here we can derive 1 for e to the minus x, right? So we can do that. And so e to the minus x would be equal to minus x to the n power, like that, as opposed to x divided by n factorial. So now we have a Maclaurin series for each of those pieces in the hyperbolic cosine formula. So we're going to then insert them in here. Okay, 1/2 times this plus that. And I guess it's good to just then draw an arrow here. So we have the hyperbolic cosine of x equals 1/2 times the series x to the n over n factorial plus the other one. Like that. Okay. And then let's combine these two because the indices are the same. We can do that. So, and the expressions are the same. So we have the x to the n over n factorial plus minus x to the n power over n factorial. Okay. So we already know that this expression, notice that they're equal with the exception that when n is odd, right? When n is 1, 3, 5, 7, and so on, these two are exactly equal and opposite in sign. So we already know that this quantity adds up to 0 for n equal odd. So let's write that. That we know that from this exercise, right? And also we could just look at this and see it. So this validates what we already knew. So we already know that the add up to 0 when n equals odd. So, and this being a series, we're adding, we don't want to add zeros, right? So we only want to add the non-zero terms in this series. And so we only so we want to calculate the series for n even. Or n equal even numbers. Okay. So that means because n is incrementing from 0 and then 1, 2, 3, this incrementation is going through all the odd and even numbers. And we want to restrict that sum to go just with the even ones. How can we achieve that, right? So because of that, so to ensure adding for which n is even, we will replace wherever we have n, wherever we have n, how can we ensure that that will just generate even powers or even factorials here? Our main concern being that. So this, if n equals 0, then, so that doesn't matter, but for n equals 1, we want that 1 to be even, so 2. For 3, we want that to be even. say 6. For 1, we want it to be 2. For 3, we want it to be 6. For 5, we want it to be 10, and so on. So we want to get rid of any odd power terms here. Okay, so for that, let us, to ensure that, one way to achieve that is we will replace n, and let me call this equation 1. Equation 1, and I'll label it like that. Equation 1. We will replace every n in equation 1 with 2n. Okay, that guarantees that our series just adds those the even values. Okay, so then let's do that here. So we have 1/2 and summation n goes to from 0 to infinity of, instead of x to the n, we have x to 2n power, and divided by 2n factorial plus minus x, right? Instead of n, we have 2n. Now for x equals, or for n equals 0, that'll be just 1. The algebraic, the minus drops out. For 1, n equals 1, that'll be 2, so the algebraic minus drops out. For n equals 3, again, that power is even, and that drops out, and so on and so forth. Divided by, once again, replace that by 2n factorial. Oops, sorry, I was way down here. So I simply replaced every n in the previous, in equation 1, with this, with 2n. Okay, so now we can get rid of this minus because of this 2. So we will have 1/2 plus, we're just going to write as x to 2n power over 2n factorial. Okay. And then a little bit more. So this will be just 2 times x to the 2n power like that, since we have common denominator, and then over 2n factorial, of course. Now, this 2 and this 2 cancel each other out, and we are left with x to the 2n over 2n factorial. So this is our Maclaurin series representation of hyperbolic cosine of x. Okay, so now we have to find the radius of convergence, which means we have to apply the ratio test. So for this series, right? I think maybe in the next examples I will skip writing this because I'm sure you know it by now. So I won't bore you with this detail anymore. I'll just go right to it. So like that, n plus 1 over an. So then let's replace everything So we have x to 2, replace the n with n plus 1, divided by 2 times n plus 1 factorial, right, times, now flip that. Since we're dividing by this whole thing, we can flip that. And we have this x to the 2n inside the absolute value. So then we can write the limit as n goes to infinity of x to the 2n plus 2, right? Just distribute that, divided by 2n plus 2 factorial. Times 2n factorial over x to the 2n. So there are terms that we can cancel. After we do that, we will end up with so this x to the 2n and this cancel each other out. That and that. I don't want to, maybe lightly I should do that. I don't know if I want to cover these with that. So we're left with x squared. And this, well, let me write it out just to make sure that everyone is following this. So x squared. We can expand this factorial, right? We can write it as 2n plus 2 times 2n plus 1, because every time we're subtracting 1 from this. And then times 2n factorial. Sorry, 2n inside the parentheses factorial. Right? That's that. Then times 2n factorial divided by 1, since that is gone now. Okay, so now this will go, these two will cancel out, and we are left with limit as n goes to infinity of x squared divided by 2n plus 2 times 2n plus 1 inside the absolute value. So of course this x squared can be brought outside of the absolute value, and because it's x squared, we don't even need to put it inside the absolute value. So we have x squared times limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. Okay, so we know that that term drops to 0. 0 times x squared is just 0. Is 0, and we know this is less than 1. Less than 1. And this is, of course, irrespective of any x, which means this is true for all x. And therefore, our radius of convergence is infinity. Like that. Okay. So let us do another type of example. So here we want to find a Taylor series for f of x centered at the given value of a, in this case 2. Assume that f has a power series expansion, which of course is necessary for us if we want to apply the Taylor series. Okay. All right, so let's recall first of all, let's write down the general Taylor series formula. Okay, so we have Taylor series is as follows: f of x equals at a divided by n factorial times x minus a to n. Okay. So we have a equals 2, right? So therefore, we have the f of x equals natural log of x would be equal to, so f of the nth derivative of function at 2 divided by n factorial times x minus 2 to n power. Okay, so once again, let us find a pattern for this, because that is clear what it is. This is clear what it is, but we really don't have any idea for that expression. It's just the nth derivative evaluated at 2, and we need an expression for that. So just like before, let us find a pattern for this. Or a general pattern, right? It's implied here. Find a general pattern for the nth derivative evaluated at 2. To do that, we'll have to, of course, take this function, calculate its derivatives several, first, second, third, fourth derivatives several times, or several derivatives of this function, and then evaluate each one at 2 to see what kind of a pattern we get. So let's do that. We have, let me see, maybe I can put that here. Okay. I think my table is too big because we don't need the natural log of x has a clean small derivatives, so we shouldn't need that big of a table. So f is nth derivative at x, and then of course nth derivative at 2. Okay, let's do maybe 5. Or 5 or 6, so I'll do 0, 1, 2, 3, 4, 5. Let's see how that will turn out, and of course this will go on. And so the nth derivative when n equals 0, that refers to the original function, so that is natural log of x. When n equals 1, that refers to the first derivative of natural log of x is 1 over x. Then when n equals 2, that would be the second derivative of that, or the next derivative of this, which is minus 1 over x squared. Right, minus 1 over x squared. And then the third one would be, I've already calculated these, so this would be 2, when n equals 3, is the third derivative of natural log of x, and it would be 2 over x cubed. Because this is not a lesson about derivatives, so I'm going through these quickly. So if you have any questions about this, please come visit me during office hours. And then for the fourth derivative, we have minus 6 divided by x to the fourth. For the fifth derivative, and then for the fifth derivative, I have 24 divided by x to the fifth power. So I guess I'll stop there, but we can continue. Okay, so each of these evaluated at 2, what do we get for the first one? Natural log of 2. For this, we get 1 over 2. For this, we get minus 1. I don't want to calculate these as 4 because we're looking for pattern, I want to write them as 2 squared. That way we can keep track of the patterns. And then for this one, 2 over 2 cubed. For this one, minus 6 over 2 to the 4th. And for this one, 24 divided by 2 to the 5th power. Okay, like that. So these will help us find a pattern. So, so using these, I guess let me put that here. These few ones, right? These few values. We will find, we will write the first few terms in the series. So let's do that. So using these, we will okay. All right, so let's do that. And I'm just using that, replacing the numerator with the values that we have. That's all. For n equals 0, for n equals 1, and so on. So we have, so we have natural log of 2. That's for n equals 0. So you can see it still on the screen here. For n equals 0, that is natural log of 2 divided by 0 factorial, right? Well, let me actually write it. So I'll write the Taylor series here. So you have it on the screen as we go through this, like that. So natural log of 2 divided by 0 factorial. And then times, of course, x minus 2 to 0 power, right? And then the next one will be plus 1, and this will be 1/2. Okay, so we will have, and then 1/2 2 times n factorial, n being 1, so it would be 1 factorial times 2 to the 1 power. So 1, that's just that one, divided by 1/2, 2 times, it's just 1/2 divided by n factorial. So it will be, n factorial would be 1 factorial. And then we have the 2 here would be 2 to first power, right? Since I wrote 2 squared, 2 cubed, 2 to the 4th, 2 to the 5th, I just wrote 2 to the first power. So I'm just going to write 2 to the first power here, because we are looking for this pattern. And we're going to generalize it. X minus 2 to first power. Then plus, the next one is minus 1 over 2 to the 2 squared. So we will say plus minus 1 divided by, and this is the second term, so it will be 2 factorial. And 2 squared will be 2 squared. And then times x minus 2 cubed. 0, 1, 2. So let me see. So this should be So this should be 0, 1. So sorry, this would be squared. Okay, like that. And then plus, I'm going to have to come down here. We can write, can I fit another term? Maybe. So I'll just write, that's this one, this term, for which n equals 3. So we have 2 divided by 2 over 2 cubed divided by n factorial. So that'll be 3 factorial times 2 cubed. That 2 cubed is this 2 cubed. This, I'm dividing, this numerator is that. So I'm dividing that by n factorial, and I'm simplifying at the same time. So I'm getting that. And then times x minus 2 cubed. Cubed, like that. Okay? And then let me continue here. And then for the next term, we have minus 6 over 2 to the 4th power, right? So we have minus 6 divided by 2 to the 4th, minus 6 over 2 to the 4th divided by n factorial. We get, that will be 4 factorial. Since this is the 4th term, that would be 4 factorial times 2 to the 4th power. Do you see the pattern? The pattern is emerging. Looking at this, you can definitely see a pattern there. And then x minus 2 to the 4th power. And then lastly, that's last one is 1. I never did this one. I never did n equals 6. So I'm just gonna, so that's just a dot. All of this is for, this last row is for n equals 5. So we have, that one is 24 divided by 2 to the 5th power. So we have, I'm just going to put 24 here divided by, that would be the 5th. Well, you can barely see it. It's off the screen. But this is the 5th term. So we have 5 factorial times 2 to the 5th. Right? Because I'm dividing all of this term by n factorial. And after you simplify it, you get this. Okay? And then times, of course, x minus 2 to 5th power. And then, of course, plus the rest of it, which we're not going to calculate. Because this is enough. This will tell us the pattern that we were looking for. So then we have, let's see what, let me grab that. Let's simplify this a little bit with a general pattern. So we have our initial function, natural log of s, or let's call it f of x, equals, that's just natural log of 2. I mean, there is no pattern connected with this and the rest of this, so we're just going to keep this separate, this piece. Natural log of 2 plus, then let's put, the pattern starts, it seems, here. So we're just going to put a series notation, start our series notation here. Then we have, well, let me correct myself. Since, so this is n equals 0. N equals 0 is that. So this one will be n equals 1. Right? So my series is starting at 0? No. This should start at 1 because that's where we're starting the sum. So n equals 1 rather than 0. And then let's see. We have an alternating terms, right? Minus 1, 1. And then we have, again, minus 6 here. Did we have, let me see if we had minus, so we have, yeah, minus 1 and then minus 6. So that should be enough. That should be good enough. So we need a term here that will give us the alternating algebraic sign. And that would be, if we have n for 0, that would give us the positive. For this one, it would, if n equals 1, it would be negative, but it's positive, so it would not work. So n plus 1 should work then. And then for n equals 0, for n equals 0, let's see. We don't need that. For n equals 1, because we already have that separately figured out. So n equals 1, this would be just minus 1 squared, which is positive, which is what we want. Okay. And then for n equals 2, which is that, we should have a negative sign. 2 plus 1 is 3, minus 1 cubed, the minus 1 algebraic sign is preserved, and that's what we want. And the next one will be again even power 3 plus 1, and then it'll negative 1 drops out. So this is good. And then the other terms that we need to generalize are, well, this one is already for x minus 2 for n equals 1, x minus 2 to first power, x minus 2 to second power for n equals 2. So that's easy to figure out. And then we also need a way to model this. We're going from 1 to negative 1 to 2, negative 6, 24. So that will be if we have n equals 1, no, that wouldn't work. N plus 1, that would not work. N minus 1, so we have, let's see, and then, well, 2 minus, well, the minus has already been taken care of, but 1, 1, and then 2, 6, 24. So we're looking for a pattern for just to model the numbers, not the algebraic sign, which is captured here. And so that would be n minus 1, so let n minus 1, right? So for n equals 1, this will be just 0. Oh, n minus 1, so that wouldn't work, so we would need n minus 1, and then, so factorial there. Yeah, that should do it. So n minus 1 factorial, when n equals 1, that would be 0 factorial, which is 1. For n equals 2, that would be 2 minus 1. That would be 1 factorial, which is 1, times, and 2 plus 1, minus 1 here. So, and that should, 2 minus 1 would give us that. And for n equals 3, this would be 3 minus 1, 2 factorial, which is 2. For n equals 4, that would be 4 minus 1 factorial, or 3 factorial, which is 6, and so on and so forth. So this should work, divided by, so this is what we just basically do. After we've listed a few terms of the Taylor series, we just look for a pattern, that's all. And divided by, of course, let me not forget that, x minus 2 to n power, divided by, so for, this is n, this should be n factorial, for n equals 1, n equals 2, n equals 3, n equals 4, n equals, so that's easy to figure out, n factorial, and then 2 squared, 2 cubed, so 2 to the 1, so this will be times 2 to the n power. And that should do it. So that's that, but of course we should, since we have an n minus 1 here, factorial, and an n factorial, there are things we can simplify. So let's do that. So we have the then natural log of 2 stays, and plus, so we have the series, and then we have the minus 1 to n plus 1 power, n minus 1, and then we can expand this a little bit. So n minus 1 factorial divided by, let's expand this, we have n times n minus 1 factorial times 2 to the n. And of course that stays. So now we can cancel these terms, and we end up with so natural log of x, which is the function we're approximating with Taylor series, equals natural log of 2 plus, like that, and then minus 1 to n plus 1 power times, we simply have then 1 over n times 2 to the n power, that, and then of course x minus 2 to n power. So this is our Taylor series approximation of natural log of x. Okay, then we also have to find the radius of convergence, and for that we will take the ratio test. So like that, we have so everything there replaced, every n replaced with n plus 1, right? So for this case, it will be, there is no n here, so we don't need to worry about that. We just keep it out. And then this series, let's see what is the radius of convergence. For that, it would be minus 1, 2. I'm just going to do this at the same time. Replace this with n plus 1, right? That's what we're doing. So we get n plus 2, and then times x minus 2 to n plus 1 power, divided by n plus 1 times 2 to n plus 1 power, and then that multiplied by this expression flipped upside down. So we have n times 2 to the n power divided by minus 1 to n plus 1 times x minus 2 to n power. Okay, like that. Okay, so let's simplify things. So the minus 1 to the n and the minus 1 to the n cancel out, but the minus 1 we will have minus 1 to power 1 there, but that also gets cancelled when we have the absolute value. Nonetheless, let me include it. But it's going to drop out, and then times x minus 2 to n plus 1 to the n power and to the n power and cancel out. We end up with just x minus 2. And here we have n. It doesn't cancel with anything, so we write it down. And then what about 2 to the n? 2 to the n cancels with 2 to the n piece of this, but then we will have 2 to the first power there, which is 2 remaining. So that will stay here. But 2 to the n's drop out. And then what else we have? We have n plus 1, and n plus 1 stays. And what else? That's it. That's just about it. So that simplifies to that. And then, so this, as we said, this minus 1 just cancels away. X minus 2, we can pull that out inside the absolute value. And also the 2 here, let me pull that out of the absolute value. So then we will, our limit will contain n over n plus 1. right, like that. So now, just using the method we used in the previous section, 8.6, we can figure out the limit of that pretty easily. Let us divide every term by the highest power of n in the denominator. So we have n over n plus 1 over n. And then so we have 1 over 1 plus, of course, 1 over n, which drops out as 0 when we apply the limit. So we will get 1 from here. So we'll have absolute value of x minus 2 over 2 times 1. And that's just equal to absolute value of x minus 2 divided by 2. And this is, so we can easily then conclude that for this series to converge, we must have, the ratio test must have that this quantity, x minus 2 over 2, must be less than 1. Right? That's the condition based on the ratio test. And so we have absolute value of x minus 2 less than 2. And so that's what they're asking, is just the radius of convergence. So the radius of convergence is 2. Okay. So I'm sure it might require you, if you're new to Taylor series and this type of material, then it may require you to look at these examples more than once, and that's quite normal. If you have to do that, please don't get discouraged. Just look at it again, try to rework these examples on a piece of scratch paper again, and see each time you will see the procedure better and better. Okay, so let's look at another example here. So this is, again, we want to find the Taylor series approximation of this at a equals pi over 2. Okay, because we do have a Maclaurin series approximation of this in our table. But this is the Taylor series approximation at a equals pi over 2. So the Taylor series, the general one, the Taylor series, tells us that the series approximation of a function should have this format: the nth derivative at a, which is in our case is pi over 2, divided by n factorial times x minus a to n power. Okay, so again, these two terms we have no issues with. A is pi over 2, n factorial is just, it looks back at the index of the series, no problem. This is the issue that we want to resolve, the numerator. So the way to start again is find a few of the derivative of first, second, third, fourth, fifth derivatives of this sine of x. And with this function, it should be pretty easy to do. And then evaluate those derivatives at pi over 2, and then look for a pattern that we can then generalize and insert in the numerator here. I hope the procedure now is sinking in. Maybe at this point, after having done a few examples, maybe you want to pause the video and finish this example on your own and see if your solution agrees with mine. That would be very interesting for you. That would be a quick check as to how much of the procedure so far you've been able to follow. So please pause and finish this answer this problem on your own. Okay, and then so I will, to figure out the pattern in the nth derivatives of the function, I'm just going to set up a small table here because the derivatives of sine of x are pretty clean and small. Something like that should be sufficient. And then we have, just like before, I will list the derivatives at pi over 2 here, the derivatives at x here, and our n's on the left side. So n, and this would be derivatives at a, and then at pi over 2. Okay, so I guess a few would be enough. I mean, 0 to 4 should be more than enough because this will repeat itself. We can continue, of course, but no need to. So when n equals 0, it refers, this notation refers to the original function, right? So we have sine of x. Then when n equals 1, it's the first derivative of sine of x, which we know is cosine of x. When n equals 2, it refers to the second derivative of that, which is the next derivative of this, which is minus sine of x. When n equals 3, it refers to the third derivative of that function, which would be the next derivative after that, and that would be minus cosine of x. And when n equals 4, it refers to the fourth derivative of that function. And so we have, or the next derivative of this, which will be just positive sine of x. Okay, so at pi over 2 sine of x, sine of pi over 2, it'll be 1. It's 1. Cosine of pi over 2, 0. Minus sine of pi over 2, it's minus 1. Minus cosine of x, or cosine of pi over 2, is just 0. Sine of pi over 2, again, it goes back to what we started, which is 1. So, of course, this can go on forever. Okay, so we have then, from here, we can write f of x equals the series from 0 to infinity of that nth derivative at pi over 2 this time, divided by n factorial times x minus pi over 2 to the n power. Right? So we have that. So as you can see, like the other one, like the other example we have derivative terms at pi over 2, which are 0. We don't want to add those in our mix, in our series that we're putting together. So we can skip those. So let me write that down. So let us calculate the first few non-zero terms of this series. Okay, we will do that. So let's see. We have f of x equals, so if n is 0, we got that term will be 1, the whole numerator. So 1 over 0 factorial, which is 1, so we get 1. 1 times n equals 0, that whole thing becomes 1. So it's non-zero, so we want that, 1. If n equals 1, we got that term 0, right? That numerator term. So we don't want that because that whole thing is 0. So let's go to the next one. When n equals 2, what did we get? We get -1. So it's a negative, so minus, so that thing is minus. -1, that whole thing is -1 times that, right? So we can write x minus pi over 2 to the n power divided by n factorial. And for that would be 2 factorial because we skipped when n equals 1 because it's just 0. So we have 2 factorial. Okay? For n equals 3, again we have 0. Do we want that? No. We will skip it because we already know for n equals 3, this whole thing is going to be 0 because the numerator here, we've determined it's going to be 0. So we'll go to n equals 4. For n equals 4, the numerator here, we calculated in our table, is 1. So 1 over n factorial, so it's going to be a positive term. So plus x minus pi over 2 to n, well, I should actually put this, n was 2, right? So let me correct that. So this n should be 2. 2 factorial, so this would be 2. So this is 2, not n. Sorry about that. So this one is the fourth, n equals 4, so let me not forget and put 4 there right away. And of course it's positive, divided by, because this is positive, 1. 4 divided by 4 factorial, right? So did we calculate n equals any expression for nth derivative of pi over 2 for n equals 5? No. But we already know, looking at the pattern here, for odd n equals odd, the nth derivative term is 0. See, n equals 1, 0. N equals 3, 0. So we already know that for the fifth, when n equals 5, it's going to be 0. We don't want that. So what about when n equals 6? Do you think we can include that here? Absolutely. Look at the pattern. Positive, negative, positive. I didn't do that in my table, but we already know it's going to be -1. We already know that. So just, you can see a pattern emerging here. So minus, and remember we skipped n equals 5 because it would be 0. We already know that, given that. So x minus pi over 2 to 5th power divided by, to 6th power, because this is the n equals 6 we're calculating. Not calculating, but writing it down, looking at the pattern of the terms we have so far, and then over 6 factorial. And of course, after that we have positive, and then ... So the term that has 8 factorial, looking at the denominators, the pattern that they have, the 8 factorial would be positive, just because of the pattern we have. Okay. So now that the pattern is clear for us, let us write the series. So we have then thus, we have the sine of x is equal to the series from 0 to infinity of, look at the pattern of algebraic signs, positive, negative. So this is n equals 0. This is n equals 1. So -1 to 0 power, -1 to 1 power. Well, no, this is the n equals 2. So let me, so just looking, well, we can just look at this and write down the pattern. It would be looking at these terms in the series, never mind the ones that reduce to 0. We can write -1 to taking this at 0 as n equals 0, and then this at n equals 1, so this should be n. So that should give us the correct algebraic sign there. And then, of course, those are easy to write down. Then this would be n. I guess if this is n equals 0, this is n equals 1. Never mind these. Never mind these n's anymore. Now this is the series we have. We've excluded the terms. If you still look back at this, it'll give you terms that are 0. No, we're done with this. We're looking at this pattern and writing our series. Because all the terms that end up being 0 are excluded. So looking at this is our first term. This is n equals 0, n equals 1, n equals 2, n equals 3. This is how you should read this. Don't look back at this anymore, okay? Because this will give you the 0 terms too, and we don't want that. So for n equals 0, and then n equals, so this would be n equals 1, and the power is 2. So how do we generalize that? 2n should do it, and then this being the n equals 2, 2 times 2 is 4. This being the third term, n equals 3, right? N equals 0, n equals 1, n equals 2, n equals 3. 2 times 3 gives us the right power, 6. So this power is 2n, and it generalizes the correct power for each term in this series. Divided by, take a look at this. So now how do we generalize that? The same way we generalize this, because these match, right? So instead of 2n, we write 2n factorial because of the factorial that we have. Okay, so this series here is a Taylor series of sine of x at a equals pi over 2. At pi over 2. Okay? Now let's look at the radius of convergence. We will apply the familiar ratio test. So every n here will be replaced with n plus 1 to obtain this, and then multiplied by flip this whole expression. So we have minus 1 to n plus 1 power times x minus pi over 2 to 2 times, let me simplify this at the same time. So instead of 2 times n, we will have 2 times n plus 1. So when you distribute the 2, you get 2n plus 2 divided by, and this will be again 2 times n plus 1 factorial. So distribute the 2, you get 2n plus 2 factorial. Like that. And then times, of course, this whole fraction or expression flipped upside down. So we have 2n factorial divided by minus 1 to n times x minus pi over 2 to 2n power inside the absolute value here. Like that. Okay. So then, of course, there are terms we can simplify. So we can expand this. Let's do that. We have So we can, well, let me keep that also. Well, the minus 1 to n power and minus 1 to n power cancel out, so we end up with just minus 1 to 1 power. And then we have x minus pi over 2 to 2n plus 2. This is what I want to simplify a little bit. So let's expand this for a few terms. 2n plus 2 times 2n plus 1 times 2n factorial, which is what we want, considering that it can cancel with that. And this minus 1 to the n and this minus 1 to the n, I've already canceled. This is just minus 1 to the first power remaining. So I'm just going to write down that piece. And that I should have canceled that too, but I will do it next. It's okay. Okay, like that. So now clearly that and this cancel each other out. That's going to drop out because when we take things outside of the absolute value. So we have these two will remain, and then this x minus pi over 2 to the 2n power, and this will cancel out. We will just have x minus pi over 2 to second power. Okay, so let me write that next. Okay, so we have so that will go away. We will have just x minus pi over 2 squared, and then divided by all of that. 2n plus 2 times 2n plus 1. So the value of that. Okay. So now we can bring this whole term out, and it's squared, so we don't need the absolute value around it. And so we have x minus pi over 2 squared, limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. Of course, we don't need the absolute value anymore because everything here is positive. So this is an easy limit to calculate. This will drop down to 0. So we will have x minus pi over 2 squared times 0. And then we will get 0. And by the ratio test, notice that this is independent of any x values. So this is true. So the convergence happens for all x. And that means that radius of convergence is infinity. Okay, so this will, and this is the end of that example. Let's do another example. So here it's asking us specifically to use the binomial series to expand the function as a power series. State the radius of convergence. Let me, if I can, I think it was page 5. I've marked it on that page, and it's the last one in that table that we have. So let me bring it back again. It is that one, this one at the very bottom of the table on page 5. Okay, so this is the binomial series. They want us to apply this, which means what? Which means we have to write this expression in this form, 1 plus x to some k. or 1 plus some term in x terms, in terms of x, to k power. Okay? Right now, our expression does not look like that. A lot of mathematics is just visual arts. So visually, we have to rewrite this so it looks like this expression or something similar to it. Especially the 1 has to be there plus some term in x or something in terms of x to some power. And then we can apply this Maclaurin series formula for it. And then this k choose n, we will use this definition of that. Okay? This definition of that. Okay. All right, so, and I will refer back to it for the sake of your notes. So, I will write down what I just said, that we will refer back to the table. So the binomial series is as follows. I'm just going to write down what I showed on that page. 1 plus x to k equals a series from 0 to infinity of k choose n times x to the n. And this is for any real number k. Where absolute value of x is less than 1. All of this is in that table too. Okay, and I will, just for the sake of your notes, so you have a complete set of instructions on this page, I will say that we will use this definition. It's also mentioned in your book, k choose n. We will use this definition to expand it. Over n factorial. Okay. All right. So let us first rewrite our expression. So we have, I'm just going to put an arrow here. Okay, so rewriting that, we will have now equals, let's factor the inside of the radical. We have 8 times 1 plus x over 8, of course. Right? That's just that. Because we want that 1 there to make our expression like that. 1 plus some x term, or some term in x. Then this is, we can rewrite 8 in terms of 2 powers of 2, which is 2 cubed, so that's helpful. So let's do that. 2 cubed times 1 plus x over 8, like that. And then, of course, this 2 can come out in front. And let's put the rest of this in terms of rational exponents. So 1 plus x over 8 to 1/3 power, right? So now we have some expression that looks like that, with k being 1 over 3 and x being x over 8. And of course, that's going to give us the radius of convergence. So that's going to, this ratio, right? In the original binomial series, x, absolute value of x is less than 1. That's how we calculate the radius of convergence here. X over 8 should be less, or absolute value of x over 8 should be less than 1. Okay, so we already know the radius of convergence, right? It's 8. Okay, but we'll get to it later. So now let us calculate if, let us first set up the binomial series for this, because this is rewritten version of this, so we can apply the binomial series, and let us do that. So you can see it here. Let me actually, I want this to stand out, so I want to box it here. All of that information is very helpful for us. Okay, so we have, I'll start with this. Equals, I'm just going to put this 2 in front of our series. So 2 times the series from n equals 0 to infinity. And then k in our case is 1 over 3. So we have 1 over 3. And then n is just n as we increment it here. And then we have times x, not x, but in our case it's x over 8 to n power. So we have x over 8 to n power. Okay? So having this helped us set up the binomial series for our expression here. Okay, so, but we still need to figure out the rest of this. So let us expand a few terms from this series. Okay, so I will just start it from here. So this 2 in front, I'm going to keep it outside. So we will have, let's do from n equals 0 to n equals 3. So we have 1/3 choose 0, and then we have x over 8 to 0 power plus, right, 1/3, and then this is for n equals 1, and then x over 8 to power 1 plus 1 over 3. This is the second term, so n equals 2, not the second term, but the third term, for which n equals 2, and then x over 8, second power, plus, maybe I can fit another term here, 1 over 3, and then, let's see, so it will be 0, 1, 2, 3, and then this will be x over 8 cubed. And then, of course, I'm running out of room there, but it's plus dot, dot, dot. So we can continue forever if we have the time. Okay, so now let us use this expression to expand all of this term. 1 over 3 choose 0, 1 over 3 choose 1, 1 over 3 choose 2, and so on. We're going to use that. Okay? So when we do that, and I will write it again here because it's off the screen. So let me write it again at the expense of course, I know I'm being redundant here, but you should see that. Since we're just introducing this topic, I want to make sure that you see that, like that. So we're going to apply this expansion to this term, to this term, this term, this term, and so on and so forth. Okay, and this term, of course. Okay, when we do that, so I'm going to start from here, 2 times, all of this is just 1, 1 times 1 is just 1, so we get 1, that's easy, 1 plus. Now this, we will have 1 over 3, choose 1, that's just 1 over 3, times x over 8 to 1 power is x over 8. So we're going to have 1 over 3 times x over 8, like that. And then plus, now here I have to be careful. This is when n equals 2, right? N equals 0, n equals 1, n equals 2. So we have 1/3. I'm just going to use that. This is what we're expanding, right? So k, this is k, 1 over 3 times the next one, k minus 1. That is 1 over 3 minus 1. 1 over 3 minus 1, I'm expanding according to this formula. We get, what do we get? We get minus 2 over 3, right? 1 over 3 minus 1. We get minus 2 over 3. And then so that divided by 2 factorial, right? So 2, let's see, yes, 2 factorial times, of course, x over 8 squared, like that. So the next term we have k being 1 over 3 again, times k minus 1. We already calculate that. That's minus 2 over 3. Notice that this is going to k minus n plus 1. So we're going to calculate how many terms? We're n equals 0, n equals 1, n equals 2, n equals 3. So we're going to calculate 3 or equal number. So n is equal to 3. We're going to have to calculate 3 terms here. So k times k minus 1 times k minus 2. K minus 2 would be 1 over 3 minus 2. And I'll just leave you to verify my number, but this will be this term. So let me say this again. This is the result of n equals 3. So we have to calculate 3 terms in this expansion for k choose n. So 1, 2, 3. So that would be, we already have these 2. We need to calculate another one. That would be 1 over 3 minus 2. When we do that, I got minus 5 over 3. And please double check that. And then, of course, this divided by 3 factorial times x over 8 cubed, right? Just like that. I'm running out of room there. Cubed, and then again, plus dot, dot, dot there, and close bracket. Okay. All right. So now, let us calculate these things and put them in a form that is easy to distinguish the pattern for. So notice that we have, these two, we can rewrite these very quickly. So let's do that first. So equals 2 times 1 plus, that's just x over 24. Sometimes I think about keeping them separate because that way it's easier to determine the pattern. So maybe I should do that. Let me keep them separate for now. 3 times 8. And then plus, notice that there is a pattern here because this is minus 2 divided by 3 times 3 or 3 squared. And then that's a complex fraction. So let me actually do that. Let me write it that way so you can see it better. So I'm going to rewrite this as this. Minus 2 divided by 3 squared divided by 2 factorial times x over 8 squared. Okay? Plus, look at these. We have minus 2 times minus 5, right? Never mind the 1. But minus 2 times minus 5, and let's keep them separate. I don't want to write down positive 10. So minus 2 times minus 5. And then look at the 3's. How many 3's we have? We have 3 cubed, right? So divided by 3 cubed divided by 3 factorial times x over 8 cubed plus all of that, the rest of it, which we didn't calculate. So now, do you see how we can simplify this? We can bring these are just complex fractions. We can easily put these 3 squared multiplied by 2 factorial, 3 cubed multiplied by 3 factorial, and so on. So let us do that. We have equals 2 times 1. This time I'm going to just write down x over 24. I don't think there is any harm doing that. But here, we can benefit great. Now the pattern starts here. So I'm going to include these two and whatever comes after it as part of that series that we're looking for. So, and this was n equals 0. Let me write that down. So the question is, what should be the index of this series? Because we already have 2 terms here. Well, this is n equals 0 is that. N equals 1 is that. So n equals 2 is that, right? And we're starting our series from here. So the index should start from n equals 2 to infinity. And then let's simplify this complex fraction. We're going to have minus 2, minus 2 divided by 3 squared times 2 factorial, right? If you simplify this complex fraction, you're going to get this. Times x over 8 squared. And then let's do the same thing here. We're going to simplify this complex fraction. Plus, notice another pattern that is emerging is the alternating signs. Okay, so this is an alternating series. And then, so this is minus 2, I'm still going to keep it separate, minus 2 times minus 5, divided by 3 cubed times 3 factorial. And of course, times x over 8 cubed plus the rest of this. Okay, and we don't need that sheet anymore. Okay, now the question is, we know we have an alternating series, so how do we model that? Let's come down and do that here. So 2 times, we have 1, we have x over 24, then we have this series starting from n equals 2. So we have n equals 0 gives us that, n equals 1 gives us that, positive, positive. Then how about this one? This is the n, for n equals 2, we get a negative. For n equals 3, we get a positive, right? This is positive 10. So we have to have minus 1. This is for even terms, we're getting a negative sign. For odd terms, well, I mean, for when n equals odd, we get positive. When n equals some even number, we get negative. So then that should be n minus 1 should do that. So 2 minus 1, right? 2 minus 1 is 1. Minus 1, we get negative. For n equals 3, we get 3 minus 1, 2, which is even. This drops out. We get positive. Good. So this will do the job. Then the question is how to model these numbers, not the algebraic signs, never mind the algebraic signs, but the 2 and the 10 and whatever comes after that. Well, we already have, notice that we already have the next term. It takes whatever that digit is, multiplies it by 5. So what is the pattern there? So 2 times n, or 2 times the previous one plus 1. Well, this is how we can figure that out. So multiply, so 2 times 5, right? That's 2 times 5, times everything in between, times the pattern there would be, would come to us from, let me bring back the previous page, from this expression. From this expression, knowing that the negative numbers have been factored out. Okay, the negative has been factored out to this term now in this series. So we need to calculate this to find the general pattern for how these numbers continue, 2 and then 2 times 5, and what number comes after that. We need to generalize that. To generalize that, we will use this, k minus n plus 1, but you got to keep in mind, we've already factored out the negatives in the alternating series that we have. This term handles our algebraic sign. So we need to, whatever we get, we need to factor the negative 1 from it. Okay, so let me put this back. Well, let me put the result here first, and then I'll write down. So this will be, actually, let me actually write it this way. So times 1 over 3 minus n plus 1. Okay, and I'm just this is what I'm doing. I'm looking at this last term, which is here too. That. Okay. So let us calculate that, and then I will factor out the negative 1 from it. That's what you have to remember. So I will close this then like that, and then the denominator of all of this, and I will have to recalculate this. And well, let me write here, and then I will write that next. But so we have here, we have the, for n equals 2, we have, so we have the 2, so we have 3 to some power equal to n, right? For the third term, 3 cubed. So that one is easy to model. So let me write down 3 to the n power. That's just going to give us that term. And these also are easy to get for our series because this is the n equals 2, 2 factorial. N equals 3, 3 factorial. So that's simply n factorial. Okay. Then we have, what else do we have? We have this 8 as a denominator, right? 8 to second power, 8 to third power, 8 to second power for this, for n equals 2. For n equals 3, 8 to 8 cubed. So that again, it's 8 to n power. So we can model that here. That's that. And then that's all about it. That takes care of everything we have in the denominator here. And of course, then we have to put an x to the n power to take care of x squared, x cubed, right? N equals 2, x squared. N equals 3, x cubed. So n and this power of x are equal. So we can then add x to n power here. Okay? And we're not done yet, but I'm just going to put the brackets there. This is the one we're not done with. Okay? We need to, if I leave it like that, I'll have to factor out -1 from it and write it as positive n minus 1/3, but we have to combine 1/3 and 1, right? So we can't leave it like this. So now, I don't know how, I want to write this so you guys know exactly. So let me just circle this here. So we do like this. So we have 3 common denominator, right? And then what do we have? We have 1 minus 3n plus 3, right? Equals, we have 4 minus 3n over 3. Now you got to be careful what is happening here because that 3 is already taken care of here in 3 to the n power. Notice that's 3 squared, 3 cubed, and we're going to have that for that one too. And that one, this 3 squared and this 3 cubed, notice that is what happened when we simplified this. We got that in the denominator when we simplified these complex fractions. So that 3 is this 3 here in the common denominator is already part of this. We don't have to do that. The other thing we should remember is that this term contains an algebraic sign which has to be factored out because in our series we've done that. For everything else, for all these terms, we've already taken care of that here. So we need to factor this -1 from this. So we have negative 3n and then minus 4. And then I have to remember to put this parentheses around that. Okay, so now I want to make a mention of this, that the minus and the 3 in the denominator have already been incorporated in the series. So we don't have to worry about that. This is all we will replace this by. Okay, in the denominator, part of the series. okay, in minus 1 to n minus 1 power divided by 3 to the n power. So that expression from the series already contains that information. So this is all we need to insert here. Okay, that's what I'm trying to get at. And I don't know how well I was able to explain it. But please let me know if you have any questions. So I'm just going to rewrite this whole thing with the exception that this piece is going to have just this red, what you see in red ink. Okay, everything else is going to stay the same. Okay, so we'll have 2 times 1 plus x over 24 plus sorry, I don't think I can fit everything on the screen. And if I pull this too much down, you probably, well, let me hold it there. Maybe that's better. And then we have minus 1 to n minus 1. And we have then times, sorry for these terms being so close to each other, but I'm running out of room here, so, and then now that comes here, and then all of that divided by, I might as well simplify these because this is 3 to the n and this is 8 to the n, so why not write 24 to the n, right? Let's do that. It'll save space. 24 to the n times n factorial. Okay, so I combine these two. And then, and that should do, oh, by the way, so the x to the n, I should not forget. It's right there. I almost forgot it. So let me, so that term and that term should not be forgotten. Okay. All right. So now, what else should we do to, I think this should do it. Yeah, this should do it. And then by the way, let's distribute this 2 in front. Okay, so I'm just going to clean it up a little bit here. So 2, distributing this, we get 2 plus x over 12 plus 2 times all of that, right? 2 times, oh, I forgot my, so this should be 2. N equals, it starts from 2. N equals 2, then minus 1 to n minus 1 power, and then times 2 times 5, all of that, and then 24 to n power times n factorial, and of course x to the n. Okay, this should do it, and I will box this. Like that. Okay, so the radius of convergence I mentioned earlier, it was easy to see right from the get-go, right? Because the binomial series states that whatever that x, the radius of convergence is absolute value of x less than 1. For us, that term was x over 8, right here. So we can easily just look back at that and say that the radius of convergence is absolute value of x over 8 less than 1, which means absolute value of x less than 8, which means the radius of convergence is 8. Okay, so like that. All right, so let's do another example. Here, they want us to use a Maclaurin series from the table. Specifically, we are instructed to look at the table from the table of important Maclaurin series to obtain the Maclaurin series for the given function, this one. Right? We did that, and so the Maclaurin series for e to the x is clearly shown there, it's that. And then for e to the minus x, we can simply replace x with minus x to the n power, and then multiply it by 2. Sorry, this thing moved too much. Okay, but let's do that. So from the table, this is probably a good exercise again for you to pause the video and see what solution you will get for this one. And then unpause the video and hopefully our answers agree. So from the table, we know that e to the x, the Maclaurin series for e to the x is the series from 0 to infinity of x to the n power divided by n factorial. Right? Okay, so that means for 2 times, for this term, so we already have that, but what about this term? We simply multiply for 2e to the minus x, we'll just adjust. So we'll say 2 times that, and instead of x to the n, we have minus x to the n divided by n factorial. So in other words, 2 times, let's clean this up a little bit and write it in a way that series are traditionally or conventionally written. So we have minus 1 to n power, and then x to n power divided by n factorial. Okay, now we can put them together. We have that, we have this, we can just easily integrate those. So for f of x equals e to the x plus 2 times e to minus x, we have that one. Over n factorial plus 2 times I'm already running out of room there. Maybe I'm writing too big on the page, right, like that. Okay, so now we can combine these. So let's do that. And we can, I guess, because they have common denominator and common indices and everything, and x to the n, x to the n. So we have like that, and then we have x to the n plus 2 times minus 1 to the n power times x to the n divided by n factorial. Okay, like that. And then, so let us, we can factor out x to the n and put it in front, right? So let's do that. So we have 1. I'm factoring out x to the n. So 1 plus 2 times minus 1 to n power, and then divided by n factorial times x to the n. Okay, so that'll be it for this function. And of course, from the table, we know that the radius of convergence is infinity, right? So for this, radius of convergence is infinity. So when we add them, the radius of convergence stays the same. So okay. All right. So this was a little bit shorter relative to the other problems we did. Okay, so let's do another one of these problems. Oops. Like that. Okay, so here, the function that we have this time, it's a little bit obscure when you compare it with these functions that we have, right, in the table. But we need to write this because they're saying refer to the table. So if you compare this with any other functions that we have in the table, right, with these, definitely not any of these, right? None of that, none of the, but it looks very closely to be this expression, the binomial series again, because of this power. See, when we have this square root, so we have a rational exponent, right? So we can rewrite this in a form that is similar to the binomial series out of the options that we have in this table. So let's do that. So I will just mention that also for the sake of your notes. Some people may just download the lecture notes and not watch the videos, so they know what we're doing. So first, let us rewrite in a form that is similar to an expression in the table. And let me add, namely, the binomial series. Okay, let's do that. Okay, so I'll keep it on the screen as much as I can. So let's take that. We have x squared over square root of 2 plus x, right? So we should definitely, well, let me actually write down the binomial series since I mentioned it here. I will write it here. Let's see here. Well, so we have it. So we have 1 plus. So we have 1 plus. Sorry, I have to adjust this paper to make sure that it looks okay on the screen. So 1 plus x to the k power is equal to the series from 0 to infinity, and k choose n, and then 2x to the n power. And of course, this term is important, how we calculate this term. So let me also write down k choose n, and that is equal to k times k minus 1 times k minus 2 all the way to k minus n plus 1 plus 1 divided by n factorial. Okay, so this is the series that we're going to use. Okay, so let me move this up. So okay, so let's the first thing is, notice the 1 there, 1 plus 6. We need to factor out the 2. So we have x squared divided by square root of 2 times 1 plus x over 2. Okay, and then we have x squared. I'm just going to separate the square root of 2 from the rest of this, because this piece is what's going to give us the binomial series. So x squared over square root of 2 times 1 plus x over 2 to 1/2 power. Okay, so what else we can do? We can just x squared over square root of 2, and then let me bring this whole thing up and make this power negative. And then so 1 plus x over 2 to minus 1/2 power. Okay, so this is the binomial series we have, and this is just the coefficient of that series. We can just multiply this into that. But this is our binomial series. I guess I should say binomial series candidate, right? Because we haven't yet converted it to the series that we should. Okay, so then we have, then let's, and then I will take the whole thing like that, and then we will write it in the series form. So we have f of x equals all of that, x squared over square root of 2 times, let me bring, so refer back to this. Compare this with that, with this with that. So we have series going from 0 to infinity. So k choose n. In this case, k is minus 1/2, right? Because 1 plus x over 2, 1 plus x to k, minus 1/2 is our k. And then n, and then d. Instead of x in our binomial series, in the function, we have x over 2. So x over 2 to n power. That's what we have to do. X over 2 to n power. And we already know what the convergence, radius of convergence is, because this is absolute value of x should be less than 1. So absolute value of x over 2 should be less than 1. And let me add that here too. Let me add that here as well. So converges when absolute value of x is less than 1. Okay. All right. So now let us, just like the other example, we need to have a better, this is not good enough. We have to have the terms in our series figured out. So to do that, let's write down a few of the terms, just like before, right? So we will have x squared over, I'm going to leave that as a factor in front. Oops. And for n equals 0, we have, so that will be minus 1/2 choose 0, this would be to 0 power, it'll be 1, right? So that's an easy calculation right there. So for n equals 0, this will be just 1. For n equals 1, again, it's not too complicated of a calculation. Anything choose 1, it's just itself. So we can write minus 1/2 times x over 2, right? X over 2 to 1 power 1 is just x over 2. Then plus, here we got to be careful because we need to expand this term like that. And this is, so we have to expand. So for, we've done n equals 0, n equals 1. So this will be n equals 2. So we have to make two expansions. So minus 1/2 times minus 1/2 minus 1. Two terms we need to include for n equals 2. Okay, so we got to be careful there. We do that, so first one we have, it's minus 1/2, then minus 1/2 minus 1. That'll be minus 1.5 or minus 3 over 2. So minus 3 over 2. Divided by, this is n equals 2, so this is going to be 2 factorial. And then x over 2 to second power because this is n equals 2. So we have x over 2 squared. Okay, sorry, I think I was off the screen for a little bit. At least the left side of the page. I apologize for that. Okay, so now, so I'd like to just keep track of this. So this is for n equals 0, this is what we have. For n equals 1, this is what we have. For n equals 2, this is what we have, right? Keep track of n and what happens here. Look at the denominators, 2 squared, 2 cubed, 2 squared times 2. So this will be 2 to the 6th power. Just keep track of the denominators. Okay, we need to do that before we write the final version of this series. Okay, so let's do one more term. So we have, that will be n equals 3, which means for this expansion of this term alone, k choose n, we need to have k times k minus 1 and k minus 2, three terms there, because it's going to be for n equals 3. Okay, so let's do that. We have plus, these two are going to be the same, minus 1/2 times minus 3/2 times minus 1/2 minus 2 for the third term, for the third factor there. Minus 1/2 minus 2. We get minus 5 over 2. It's 2 divided by, of course, this is the third term, so this is going to be 3 factorial. That's n equals 3. And then, of course, I hope I can fit that x over 2 to cubed, right? Let me try to fit it here. X over 2 cubed. I'm barely doing that. I hope it's legible on the screen or it can be understood, but sorry about that. Okay, and then of course plus ... as the series can continue after that. So let us then simplify these so we can see the pattern better. So that's equal to x squared over a square root of 2 times 1 plus, let's keep these separate. So minus 1/2 times x over 2 plus minus 1 times minus 3. And this time it's going to be, let me do this at the same time. So minus 1 times minus 3. And then the 2's, 2 times 2 is 2 squared, right? But then you have a 2 squared here that is multiplying by the numerator. So you have 2 squared times 2 squared, 2 to the 4th power. But that's just part of this complex fraction. So it's 2 to the 4th power multiplies when you simplify, it multiplies the 2 factorial. Okay, let me see if I can, maybe I can use this as a, let me do this on a scratch paper. So what do we have here? We have minus 1 over 2 times minus 3 over 2 times x squared over 2 squared, right, after you distribute this power. All of that divided by 2 factorial. Now simplify this. What do we get? We get minus 1 times minus 3 times x squared divided by 2 to the 4th over 2 factorial. And this is a complex fraction, right? So we can write this as minus 1 times minus 3 times x squared divided by, right? This is simplifying this complex fraction. We get 2 to the 4th times 2 factorial, like that. Okay, so when we do that, I'm going to write that simplified form here. So minus 1 times minus 3 divided by 2 to the 4th times 2 factorial times x squared. Okay, x squared. And then the last one, the last term here, would be, see, this x squared cubed gives us 2 cubed. So that's 2 cubed, and then times another 2 cubed. So we will get 2 to the 6th power. That multiplies, just like the previous one term. When we simplify it, it'll be part of the denominator. It'll be 2 to the 6th power times 3 factorial. So, and then in the numerator, we will have those minus 1, minus 3, minus times minus 5, divided by 2 to the 6th times 3 factorial. And of course, this will be x cubed. And then after that, plus dot, dot, dot. And then let me also close the bracket there. Okay. I hope that was easy to follow. But that's what's happening here. We're combining these 2's and then putting them in the denominator of this after simplifying the complex fraction. Okay, so then continuing here, we have, let's see. So just like the term before, the example before, remember what we did for that. If I can, not the example before that, but this one. Remember what happened here? We have to do the same thing. This is going to be k minus n plus 1. In our case, k is going to be, let's see, k is going to be, I guess, let's see, 2 minus 1, let's see. K is going to be minus 1/2, right? In our case. But before we had that, so we had 1/3 minus n plus 1. So we're going to have to plug minus 1/2 here, minus n plus 1, and then we're going to have whatever we end up here, the denominator is going to be part of the whole series, but then the numerator has to be factored out. Okay, because once again we have alternating series, minus, plus, minus. Okay, so we have to do that again with this binomial series. Okay, so then I guess I can distribute this now. I think I should do that. So let us see, we have minus x. This is also, this can actually be 2 squared and n factorial, so 1 so this time this piece can be part of this series too. So let's do that. So we have, let's distribute that. So we have x squared over square root of 2 times 1, we get that. And then plus x squared over square root of 2 times the series that will generalize from this term. Let me actually write it so these will be part of the series, including that one. So we will have our series here. Then this is n equals 0. That's n equals 1, right? So let me see. So for n equals 1, we're going to get a negative term. So we can generalize that by minus 1 to n power. When n equals 0, we get a positive term. When n equals 1, we get negative term. When n equals 2, minus 1 times minus 3, positive 3. So we get a positive term. So it's working out well for us. So that's to generalize the algebraic sign. Then to generalize these terms, minus 1 times minus 3, minus 1 times minus 3 times minus 5, right? So let us generalize that. I'm going to put my fraction here. Hopefully I can fit all that here. So we have 1. We don't worry about the algebraic signs anymore because that is being taken care of by this term in this series, minus 1 to n power. So just focus on the values, 1 or the magnitudes, 1, 3, 1, 3, 5, and then 1. Right? So 1 times 3 times 5 times all the way to, so we're going to generalize that pattern, right? How? Just like I explained there, we're going to use, maybe I can, where can I, oh, right here. So we're going to do that. In our case, k is minus 1/2. So minus 1/2 minus n plus 1. And then we're going to factor the minus 1 from it. So we're going to do that. So I will write minus 1/2 minus n plus 1. Okay. And then, of course, look at the x values. So this will be n equals 1, x to the 1 power. N equals 2 for this term, x to the 2nd power. This is the third term, x to the 3rd power. So that's easy to see that we have an x to the n power out here. Okay, and that's just the page number. Sorry. As much as I try to not do things that might confuse people, I manage to do things that might confuse people. That's just page number, sorry. So our series ends here. Okay, so now the denominator, let's look at the denominator and see how we can, and of course I have work to do here. But let's take a look at the denominator. So we have, this is 2 to the 0 is going to be 1. This is 2 to the 1, so 2 to the, it's, well, 2 squared, and then 2 to the 4, 2 to the 6. So we have to some even number. And by now we know how to get that in a series. It's 2 to the 2n power. So for n equals 0, this is just going to be 2 to the 0 power 1, which will be the denominator here. Good. So that works out. For n equals 2, we should get 2 squared. Do we get that? 2 times 1, 2 squared. Yes. For the n equals 2, we should get 2 to the 4th. Do we get that? 2 times 2 times 2 times, sorry, 2 to 2 times 2 power, or 2 to the 4th power? Yes, we do. And we also get that for this, 2 to the 6th power. okay, because this would be, for this term, n equals 3, and if you plug n equals 3 here, you get 2 to the 6th power, which is what we have. So this works out. What about the factorials? Well, 0 factorial 1, 0 factorial is 1, good. 1 factorial is 1, 2 factorial, 3 factorial, that's easy to get too. So we simply say n factorial here. So almost everything is completed here with the exception of this. So let me, just like before, this piece, we have work to do with it. Okay, so what we do is take the common denominator. Again, that comes from this formula we have for expansion of k choose n. That's the last term. K minus n plus 1 we have, and our k is minus 1/2. So we have the common denominator, and then we have minus 1 minus 2n plus 2. So this will be 2 minus 1 is just 1, positive 1, minus 2n over 2. Now, this 2, just like the 2's that we've already captured in this part of the series, that 2 is part of here. So no need to keep that in up here in the numerator. Also, the algebraic sign, because this is an alternating series, then the algebraic sign, the changing algebraic sign, has been taken care of by this term. So we need to factor it to make sure that it's in line with everything else here. So let's do that. So we have, then from here, we have minus, we have 2n plus 2n minus 1. The only piece of this that will go in there in the next line when I write the series, it's going to be the ones you see in red ink. The blue ones stay out. This one is already been taken care of here. This term is already been taken care of here. So this is the only piece we need to include there in our series, finalized series. Okay, so let me do that. So we will begin with that again, and then plus x squared over square root of 2 and here we go. We have the finalized version. Since I wrote it, I'm going to keep it, and then the next one I'm going to distribute this. We're going to distribute this into our series. We're not going to keep it in front like that. So let me replace that with this. And so we have one times, 3 times, 5 times, and then we have 2n minus 1. Okay, like that. And then times, of course, x to the n power, and in the denominator we have 2 to the n times n factorial. Can we simplify this? Yes, let's distribute this x squared into this. What do we get? We get x to n plus 2 power. Let's distribute this square root of 2 into this. What do we get? We get 2 to 2n plus 1/2, right? Because the power of 2 here under square root is 2 to 1/2 power. So then we will do that next. So distributing we have this next one. so this is x to the n plus 2, like that. And here 2 to the n, 2 to the 2n power plus 1/2, right? And then of course times n factorial here. And then everything else in the numerator, this stuff stays the same. Okay, so this should do it. And let me correct one error, guys, because let me see how far back I did that. It looks like okay, so up here I need to, again, this is n equals 0. So this is, our series begins with n equals 1 that we're generalizing into the series. So this should start with 1. Sorry about that. Let me correct that. I almost missed it. So n equals 0 is this term. Our series cannot start from n equals 0. It should start from n equals 1. The same thing here. This should be n equals 1. And then this one was correct. Okay, but those two were not. I apologize for that. I hope that didn't confuse anyone. Okay, so this is basically what we were, so this is, I will also write down the function here that we are modeling with this series. It was x squared over square root of 2 plus x. So we have all of that as the series that will approximate that function, or the Taylor series that will model that function. The Maclaurin series, actually. Okay, so let's see. So we have to do one more thing, which is pretty easy to do. They want us to come up with the radius of convergence. Notice that absolute value of x should be less than 1. This is for the generalized binomial series, but in our case, x was minus 1/2, right? So we will do is absolute value of minus 1/2, or sorry, minus x over 2. Let me see. Minus or x over 2. Sorry about that. Yes, x over 2. So we have not minus, but x over 2 less than 1. And so absolute value of x. And so if you're wondering where I'm getting this is what this was the function that was the basis of what we started when we started to do the binomial series. So our x is x over 2. So absolute value of that would determine the radius of convergence. So this would be absolute value of x is less than 2. So therefore the r would be equal to 2. Okay, so that is that problem. Okay, so in the next example, we will look at, it says use series to approximate the definite integral to within the indicated accuracy. So, okay, so we have an x squared. We can certainly write this piece of the integrand as a series, so let's do that. If you want to pause the video and proceed with this on your own before you see this, I highly encourage you to do that, please, and then unpause the video to compare your solution with this. So first, note that we have a series for that, but we will begin with e to the x as this series where radius of convergence is infinity. So apply that to this series. We have, it would be, so minus x squared to n power divided by n factorial equals, and let's separate the pieces of this and write it more conventionally. To n and times x to the 2n power divided by n factorial. Okay, like that. So then let's multiply x squared by this series because that's, because that's the integrand we have. So x squared times this series is what we need to do. And when we do that, this will be x to 2n plus 2 power, right? So I'm just going to integrate it immediately with that. So we will get with this piece minus 1 to n power, distributing x squared into this series, we get 2n plus 2. This 2 is this power of x, and then divided by n factorial. Okay, so now that we have a full power series expression for the integrand, we can then place this inside of our integral. So let's do that. So that dx is equal to 0 to 0.5 of that whole thing. Divided by that dx. So this is easy to integrate. Simply add 1 to this power, divide this by the new power, 2n plus 3. So let me do that here. We will have and we have minus 1 to n power times x to 2n plus 3 divided by n factorial times 2n, the new power, right? And of course, we have the integral, this term, or this quantity going from 0 to 1/2. Okay? So now this would be the series from 0 to infinity. Just substitute for x with 1/2 divided by n factorial minus this series evaluated as 0 for x. Of course, this term drops out, right? This whole term drops out. So this is just 0, right? 0 to some power is just 0. And then so we have, let's see, we have the integral as just that. I'll just write it here. So the integral from 0 to 0.5 of x squared times e to minus x squared power dx is simply equal to n equals 0 minus 1 to n power, and this you can distribute this power to 1, it's just 1. Distribute this power to 2, it'll be 2 to 2n plus 3 power, and then we can put that in the denominator because it gives us this complex fraction. So let's do that. So we have minus 1 to n power, then divided by n factorial times 2n plus 3, and then times 2 to 2n plus 3 power. This is just here because I simplified the complex fraction there. If you distribute this power to 1/2, you'll see how this works. And then that's basically the series, this definite integral evaluated as this series. Oops. Like that. Okay, so now they asked us something else, right? They said, use series to approximate the definite integral to within the indicated accuracy. So we haven't done that yet. Okay. So to do that, we will, so we have, let me rewrite that expression here so we can look at it on the screen. And we have minus 1 to n power divided by n factorial times 2n plus 3 times 2 to the n, 2n plus 3. Okay, I didn't forget any term, did I? I don't think so. Let's see. I don't think I forgot any terms. Let's see. So I'm just making sure here. Let's see. Let's see. 2n. Let's see. So 2. No, that's correct. So yeah, we shouldn't have an x in the definite integral. So this is fine. Okay, so we have then all of that. All right, so we have, let's see, so let's get each of these, each term in the series because we have to estimate this sum to a certain accuracy. So for n equals 0, what do we get? We get, it's easy to see that that would be 1, and we'll get 1 over 24, and that's, let's see, 2 to the 4. So I got one. Double check these numbers, but this is what we get, and then 0.041667 is what I got. So if we calculate the next term, n equals 1, what do we get? And we get, and let me calculate the absolute values of these, right? So did they tell us what? Right. So the accuracy that we're looking for is the error should be less than 1 over 1,000. Okay, so this is the accuracy we're looking for in our sum, which is estimating that definite integral. So for n equals 1, and let me take the absolute value of these, because we're just looking at the errors. When I do that, we're not yet adding these. I'm not adding anything. I should later, but not now. I'm just looking at these errors to see when they're going to drop below this error. This error, 0.0001. Okay, that's what I'm watching for. And for that, I'm interested in just the magnitude. So once again, absolute value when n equals 1, this will be minus 1 over 160. And we get 0.00625. Okay, so for n equals 2, we get this, and please double check these numbers. I got 1 over 1,792, and then that gave me 0.00055,804. So that's definitely less than 0.001 condition that they asked us to abide by, right? That error is less than what they set for us, not that one, not that one, not that one. So that means by the, let me look at my, so this is our series, right? Let me bring this back. So for sure, this is an alternating series, right? So, and remember in the previous section or the one before that, we talked about alternating series estimation theorem. I think that's what the name of the theorem was. Based on that, whenever, for whatever n value the error term falls below what the condition has been set for us, then that means that if we add these two, the previous terms, the error involved is going to be at most this much, okay, by that theorem, alternating series estimation theorem. Remember that? Let me just again say what that theorem is stating. It's stating that for whatever n value that you obtain an error that is less than what the error that has been set for us, then that means that if you add the previous terms, that means n equals 0 and n equals 1, the error involved in that series, in that sum, is at most this much. So for sure, then if we add n equals 0, the sum term, the series terms for n equals 0 and n equals 1, we should get some number that has an error that is at most this much, which is less than what we were asked to do. The maximum error we were asked to have in our estimation for that integral. So all we have to do is add the series terms for n equals 0 and n equals 1. Actually, let me say a few words before I do that. So note that when n equals 2, the error is equal to 1 over 1792, which is this much. Okay, I'm just writing what I said in words for those who might just read the lecture notes. And this is, which is less than 0.001. Okay, therefore, oops, sorry, let me move this up a little bit. Therefore, for the desired accuracy, you only need to add the series terms for n equals 0 and n equals 1. Okay, and this is by the alternating series estimation theorem. Okay, so that is, now I will remove the absolute value because the absolute values was just to keep track of the error. So now we'll just say 1 over 24 plus minus 1 over 60. Okay, so minus 1 over 160, and that's going to give us roughly this much, 0.0354. Okay, so that is the value of that integral estimated to that accuracy that they asked for. That our error should be, absolute value of error should be less than 0.001, and we've achieved that. Okay, the motion detector in this room turned off the lights. Let me, while I go and turn on the lights, you can think about this, how you would go about solving this. Use series to evaluate the limit. Better yet, please pause the video and work on this and then compare your solution with mine. Okay, great. The lights are back on again. Okay, so here we want to evaluate a limit, and so let's say that of all these terms, this is the term that we can write using the series, right? Using one of the Maclaurin series, right? In that table we have a Maclaurin series for that. As x goes to 0, so we know from the table of Maclaurin series that sine of x has this expansion. We have times x to 2n plus 1 power divided by 2n plus 1 factorial. Okay, so and then also a few terms here, x minus, this is also given to us in the table, so we can make use of it here, plus x to the 5 power divided by 5 factorial minus x to the 7 divided by 7 factorial plus all the rest. And of course the radius of convergence is infinity here. Okay, this is also given in the table. So let's replace in this expression for sine of x with these terms from the table. Okay, so replacing and we have, I guess I can still keep that on the screen. So limit as x goes to 0. Well, let me rewrite it again here. So sine of x minus x plus 1 over 6 times x cubed over x to the 5 power is equal to, let's replace that with these terms. Okay, let's do that. So we have x minus x cubed 3 over 3 factorial plus x to the 5 over 5 factorial minus x to the 7 over 7 factorial plus all the rest. And then we can then include these afterwards. So minus x, right? Minus x plus 1 over 6 times x cubed. Okay, so all of this and then well, all of that over x to the 5 power. So now if you check these, if you take a careful look at these, you'll see that this x and minus x drop out, or they add up to 0. Minus x cubed over 3 factorial is the same thing as minus x cubed over 6. This is plus 1 over 6 times x cubed. So these two cancel each other out. We end up with that over x to the 5 power. So let's write that down. So then limit as x goes to infinity. I guess I should have included it here too. Let me do that. Limit as x goes to infinity for that piece. And then we have 1 over, let's see, what do we have? Well, we have, okay, so this x to the 5th power times, okay, so let me do that like this. So we have x to the 5th, x to the 5th, yeah, let me write it like this. So we have x to the 5th power, that's that one, and then this is a complex fraction again, so x to the 5 multiplies 5 factorial in the denominator here. So x to the 5th power times 5 factorial minus x to the 7th power divided by 7 factorial divided by x to the 5th power. That's a complex fraction. So minus x to the 7th power divided by, simplify the complex fraction, we get x to the 5 again, power, times 7 factorial this time. And we can notice this pattern from positive, negative, so the next one for sure it's going to be positive. Notice the pattern of terms in the numerator. We're jumping, the x powers jump by odd to the next odd number, so 5, 7, 9, and then divided by the x to the 5 power stays the same, and then the factorials again jump by every odd number factorial. So this will be 9 factorial, and the next one would be minus again, since it's alternating like that. So now if you apply the limit, well, let's see. Looking at this expression, this x to the 5 and this x to the 5 cancel, right? So what do we get? We get, let's not apply the limit yet. So we get 1 over 5 factorial minus, let's simplify that. What do we get? We get x to the 7 minus 5. We get x squared over 7 factorial plus x to the 9 minus 5. We get x to the 4th power divided by 9 factorial minus whatever else that comes after that. But if you look at these terms, with the exception of 1 over 5 factorial, all the other ones have an x in the numerator, which then goes to 0, which means these values, all of them, that goes to 0, that goes to 0. Everything else after that will go to 0 too. So our limit now, when we apply it, we get simply 1 over 5 factorial, which is 1 over 120. Okay, so this is our the limit of that expression as we applied the series for Maclaurin series for sine of x. Okay. So another example. Here we want to find the sum of this series. Okay. So how would you think about how you would approach this, and maybe pause the video and work on it for 10-15 minutes just to come up with a solution. Okay, so if you look at this expression, it seems that we can combine these terms that have 2n plus 1 as their power. Right, so let me write that down here. So combining the terms that have 2n plus 1 as power, what do we get? So we get first of all minus 1 to the n power stays the same. Then combining this, since this is in the denominator, we can pull it up and say pi over 4 to 2n plus 1 power, and then divided by 2n plus 1 factorial. So we're doing the opposite of what we did for when we did a couple of examples with binomial series. Okay, so we want to find the sum of this series at this point. And looking at this at first glance, it doesn't look like anything we've seen in the table. But let me bring back the table for a second. And if we inspect it carefully, just look at it, because a lot of the mathematics is just visual arts. I think I mentioned this before. Just visually scan this, take a good feeling about what it looks like. So we have -1, so this is an alternating series times pi to n 2n plus 1, 4 to 2n plus 1, the same power, times that power factorial. Let's see if we can see that pattern anywhere in the table that we have. Well, for sure, we don't have that here. And for sure, we don't have that here. When we get to sine of x, something should catch our eye, right? Look at this. X to 2n plus 1 over 2n plus 1 factorial. But here we do have a term with 2n plus 1 power in the numerator, but nothing with that power in the denominator. So there is some difference here. If we look at, by the way, take a look at the inverse tangent one. The inverse tangent, and if I can show both on the screen, compare the inverse tangent x series with the Maclaurin series for sine of x. They almost look alike, with the exception that this is 2n plus 1 factorial, and this is just 2n plus 1. And in our case, we have 2n plus 1 factorial. So what we have is most closely resembled to the Maclaurin series for the sinus x function. So then instead of having just one term in the numerator with 2n plus 1 power, we have two terms with that power. So let's see if we can combine these two terms into one. That have 2n plus 1 as power. This is what we're going to have. We're going to have this series from 0 to infinity. The -1 to n power stays where it was. Now let's combine these in the numerator, because what we had in the table was a term in the numerator, right? We had x to 2n plus 1 power. Let's combine pi and 4 in the denominator. So we're going to write them as pi over 4, the whole thing, raised to 2n plus 1 power. So now instead of x, we have pi over 4 to that power. And then so since that is part of pi in the numerator, we can then divide the whole thing by 2n plus 1 factorial. Now, if you compare what we have with sine of x, we almost have exactly the same thing, with the exception that x here is represented by pi over 4 in our case, right? So let's make a note of that here. Is the Maclaurin series for sine of x. In the table we have. Okay. So therefore, so we can write the whole thing. Let me that here. So the whole thing is equal to sine of, instead of x, we have sine of pi over 4. Okay, so if that's the case, then sine of pi over 4 is easily obtained by remembering what we learned about this function in trigonometry, square root of 2 over 2. Okay, I hope this presentation was helpful in your understanding of Taylor and Maclaurin series, and I thank you for watching the video until this point, and for now have a nice day, and I'll see you again next time.